Good afternoon to Dr. Ford. This is our Digital Logic final project presented by Group 2. Our group members are Tan Jianshin, Oh Shuyan, Lai Shini, and me, Kishantini. For the introduction, in the modern era of interconnected systems, digital networks play a pivotal role in enabling efficient communication and data transfer. Within these networks, the ability to reliably transmit data packets from one device to another, often across multiple nodes, is essential for smooth operations and performance. This project, undertaken as part of the Digital Logic course, focuses on simulating a real-world scenario where data packets are transmitted between two computer labs using digital logic principles and circuit design tools. This project introduces a practical application of the theoretical knowledge acquired during the course, combining creativity, teamwork, and problem solving. Specifically, the task involves designing and implementing a network packet transmission monitoring system. This system facilitates the transfer of a user-defined data packets from a computer in Lab 1 to a destination computer in Lab 2 via a single cable. The simulation utilizes DEET software, a robust platform for designing and analyzing digital circuits, to model and verify the system's functionality. The design process incorporates multiplexers, MUX, demultiplexers, DMUX, counters, comparators, and clock enablers. These elements are configured to work seamlessly, ensuring accurate packet transmission, real-time status monitoring, and optional fault detection. By working on this project, students gain hands-on experience in designing complex systems, troubleshooting circuit behavior, and applying advanced concepts like synchronous counters and fault monitoring modules. But for the problem background, efficient and accurate data transmission between computers in different locations is critical requirement in modern networks. In the given scenario, computer in lab A are connected to computer lab B via a single cable. This setup requires a mechanism to ensure the reliable transmission of a user-defined number of data packets. This setup also comes with multiple challenges that includes synchronizing data delivery from the source to the destination, monitoring the status of data transmission, implementing fault detection and handling to ensure system reliability, and designing a user-friendly dashboard to display system status. That's all from me. Thank you.
So to address these challenges, we propose the design and simulation of a network packet transmission monitoring system. The key components of the solution include the circuit design, monitoring and fault detection, simulation and testing, and advanced features. So this block diagram shows the flows of data from the source computer in Lab A through the MUX synchronous counter and comparator to the DMUX in Lab B. It will also describe the clock enable, monitoring, dashboard, and optional advanced features. For the requirement, this digital logic project requires students to design a network packet transmission monitoring system creatively using a synchronous counter of T flip-flop. Students need to form a group consisting of a maximum number of 4 students. They need to prepare the project report, slide presentation, develop the circuit in a DEET simulator, and record video for presenting the project slide and demo the circuit. There's a group of 8 computers in Lab A that is connected to a group of 8 computers in Lab B. Student needs to transmit a number of packet data defined by the user from one source computer in Lab A to another destination computer in Lab B. The system has the basic components function, which are the connection between computer from Lab A to Lab B, the countout function, the comparator function, and the clock enable function. The advanced function in this circuit design are the monitoring packet transfer function, display controller concept function, password comparator function, and monitoring fault detection function. These are the components of fun display function. We have 4 input switch, which include 1 clock generator, 1 preset and 1 clear, 2 high-level logic 1 input, 1 low-level logic 0 input, 3 T flip-flop using JK flip-flop positive input, 3-bit asynchronous counter, 3 to 8 line decoder, 3 output binary display, 1 output hexadecimal display, 16 test LEDs, 1 text box, and wire. For the countout function, we have 2 input binary switches, 1 high-level logic 1 input, 1 low-level logic 0 input, 3 JK flip-flop, 1 AND gate, 3 output binary display, 1 output hexadecimal display. For the comparator function, we have the counter comparator, which has 1 input hex digit, 1 4-bit comparator, 1 low-level logic 0 input, 1 inverter, and wires. For the password comparator, we have 4 input hex digits, 4 4-bit comparators, 4 low-level logic 0 input, 4 high-level logic 1 input, 4 test LEDs, 1 AND gate and wire. For the monitoring fault detection function, we have asynchronous mode or invalid state detection, 1 NAND gate, 1 test LED and wires. For the comparator fault, we have 4 XOR gate, 1 OR gate, 2 test LED and wires. For the counter fault, we have 3 XOR gate, 1 NOR gate, 3 D flip-flop, 1 high-level input, 1 test LED and wires. Moving on to the monitoring fault detection function. For the computer on LED data transmission fault, we have 2 clock generator, 2 AND gate, 3 inverters, 2 text box, 1 text LED, wires, and 1 text box. For the computer on LED data display fault, we have 1 NOR gate, 1 text LED, and wires. So these are the clock enable functions. We have connection between LED A and LED B, which include 2 OR gate, 1 AND gate, 2 test LEDs, wires. And for the password correctness, we have password comparator, function, and wires. And for the counter comparator function, we have counter comparator, 1 inverter, and wires. For the ready set, we have 1 input binary switch and wires. For the transmission mode function, we have 1 input hex digit, 1 high-level logic 1 input, 1 decoder 2 to 4, 1 output binary display wires, 1 AND gate and wires. And lastly, the push button, we have 1 input binary switch and wires. For the monitoring packet transfer function, we have power on, which include connection between LED A and LED B, and mode data transmission OK, which include transmission mode function, and completed packet transmission, which include counter comparator function. And next is the security module OK password, which include password comparator function. And the next one is ready transceiver on, which include input binary switch. We have 1 text LED and wires for all of each function. And lastly, we have 1 text box to display the message. For the connection between computer from LED A to LED B, we have 8 clock generator, 16 input binary switches, 16 output binary display, 17 AND gate, 2 input hex digit, 1 multiplexer 8 to 1, 1 demultiplexer 1 to 8, and also a wire.
Let's introduce our system implementation, which we implement 9 system and function in our system. First is connection of computers. Next is count out counter function. Next is counter circuit controller, clock enabler function, monitoring packet transfer function, security module, sync data delivery with counter, monitoring fault detection function, and fun display. So the most basic function is connection between computers device. So the existing computer adds in LED A and adds in LED B. Each computer has a clock generator, power control, and a data generation. The data is output on the single bit output. So to design our count up counter function, we have 3 designs. First is synchronous counter, second is T flip-flop and 3-bit. Synchronous is to avoid any propagation delay. T flip-flop is because T flip-flop is very simple. When all T input are set to high, it toggles. And 3-bit counter is because 2 to the power of 3 is 8. This counter can count 8 packets from 0 to 7. The components will consist of 3 T flip-flops and control inputs. The T flip-flop J and K input are tied to logic 1 for toggle mode. The counter counts in binary from 00 to 111. Q1 toggles with every clock pulse. Q1 toggles when Q0 are high and clock pulse is active. Q2 toggles when both Q0 and Q1 are high and clock are active. So you can see in this timing diagram, the timing diagram of Q0, Q1, and Q2. Okay, so for counter circuit controller, the function is to control the transmission of defined number packets that we select via hex input from 0 to 7 from LED A to LED B. So it includes hex input, counter, clock enabler, and comparator. The rules is like this. If the current packet count is less than maximum, the clock will be active and the counter will increase and when the packet count is less than maximum. If current packet count reach maximum, the clock will become inactive. So we choose the maximum packet count, then the clock is enabled by pressing a button and then the counter increments until maximum has reached, and once maximum has reached, the clock will be disabled. The clock enabler function design. So there is 6 rules for clock enabler to function. First is power on check. At least one computer in lab A and lab B must be power on. Next, in password validation, all 4 passwords must be correct. And next is TRS ready. The ready transceiver switch must be switched to 1. Fourth is packet count. The current packet count must be less than the maximum packet number. 5 is the transmission mode. The mode must be set to mode 1, which is simplex. And then the next is push button. Push button must be pressed to activate the clock enabler. This is the triggers that initiate the clock function. So when you press 1 time, the clock counter will increment from 0 to 7. Next time, 1 to 2 until 7. So in order for the successful monitoring packet transfer function, we implement a dashboard that monitors 4 inputs, which is power, mode, password, and readiness. All 4 LED must light up before the system can start or continue the operation. This so that every time after we implement, we choose this, we can check the dashboard to see if we have correctly set up the 4 inputs. So after the user push the push button, the current packet counter will increase until reach the maximum packet count, and then the last LED, which is the completed packet transmission, will light up, indicating that the packet transmission is completed. So how we implement this monitoring dashboard function? So for power on display LED, we just pull the signal after the AND gate so that it will on when the LED will on when we open any computer in lab A and lab 2. To implement the mode data transmission simplex mode, to check if the system is in simplex mode. So we pull the signal right after the decoder so that when the binary input is set to mode 1, the LED will light up. So to know that we completed the packet transmission, we pull the signal after the comparator A equal to B. So if A equal to B are 1, the completed packet transmission will light up, indicate that packet transmission is successful. So that to know that we have correct password enter, we pull the signal after the AND gate so that after all these 4 password input are correct, the LED will light up. So to know that we have transceiver is ready for data transmission, the signal is pulled after the TRS switch. Only after the TRS switch is switched into 1, the LED will light up. So to implement this security module password, we use 4-bit comparator, hex input, and AND gate. So the working principle is like this. We need to select the password, which is 2638, so that the comparator will compare to the 4-bit input. Only if all 4 digits is correct, it will output response 1. And then the next function is to sync data delivery with counter. We have the count up counter, but to sync the counter with the data delivery, we use an AND gate. The input of this AND gate are the data generated by computer in lab A and the output of clock enabler. The data is transmitted only when both signals are active. So the output of clock enabler needs to be 1 in order for the data transmission to be successful. We also implement a monitoring fault detection function. It is to detect 2 types of error. The first type is human error. The second type is instrumental error. So the human error includes the invalid mode, which is preset equal to 0 or clear equal to 0. So we use a NAND gate. If any of a pre and clear are 0, the LED will light up. This is to ensure that the mode is adjusted to synchronous mode instead of asynchronous mode. We also implement another function to detect the human error, which is not on the selected computer on lab A. So we need to choose a computer to transmit from as source and a computer as destination. So sometimes we choose the selected computer as source, but we didn't on the computer. So this function is to detect that we have on or not the selected computer. How we do this? We do this by pulling the signal after the demarks. The logic is like this. If the computer is on, then the data will be transmitted after the demarks and the power is on. But if the computer is not on, the data is not transmitted. So the computer on lab 1 transmission fault will not dim down. So the computer on lab 1 transmission fault should be light up all the other time, only except when we push the push button, which indicates the data transmit after the demarks. So when we push the push button, this computer on lab 1 transmission fault should be dimmed down to indicate that we have opened the selected computer. So we also implement another system to detect we on the selected computer on lab B or not. So we need to choose a destination computer on lab B, but sometimes we not on the selected computer. So an OR gate will check if the Lab B data was successfully transmitted. The logic is like this. The data is not received on the 1-bit output display in Lab B. This indicates that the Lab B selected computer is not on. The next type of error we detect is instrumental error. First is comparator faulty. Let us assume A is not equal to B. So if any XOR gate detect and A is not equal to B, the OR gate will output 1. And then the inverted comparator output, which is I put an inverter after the A equal to B, will equals to 1. And second XOR gate will compare the OR gate, which is the expected output, and the inverted comparator output, which is the actual output. If the second XOR gate is 1, the LED will light up, indicate fault detected. And then the next instrumental error it detects is counter fault. So there is 4 steps to implement this system. The first is store the previous state using D flip-flop, and next we compare the current and previous state for each bit of the 3-bit counter. The output is 0 for no change, and we use OR gate to combine those XOR output. If all XOR output are 0, no change, the OR gate will output 0. The NOT gate will convert OR gate in output to signal a fault 1. So LED on means the counter has stopped. The state didn't change. LED off means the counter changed with every clock pulse, which is the normal operation. And then we also want to introduce the system implementation of this fun display. You can see the fun display as the flip-flop increase, the LED change. So to implement this fun display, we use a asynchronous JK flip-flop and a 3 to 8 decoder and LEDs. The flip-flop will toggle through states 0 to 7, with the decoder will activate LED in different patterns based on the states. A clock signals drive this sequence while preset and killer manage initialization and resets. So the asynchronous counter need to be, the pre and killer need to be 1 in order for this fun display to work.
Okay, now let me to introduce the demo of our circuit. This is our design of the data transmission circuit. Let me give an overview of our component function in this circuit. This one is the fun display function. Below it is the connection between the 8 computers in Lab A and the 8 computers in Lab B. On the right side is one of the fault detection function, which will detect the transmission error from Lab A to Lab B. This one is the password comparator function. This one is the clock enabler function. This one is the transmission mode function. This one is the counter comparator function. This is also one of the fault detection function that will detect the counter comparator fault. This one is the monitoring packet transfer function. This one is the count up function. This one is one of the fault detection function to check whether the counter is stopped counting or not. This one is also one of the fault detection function that will ensure that the counter is in the synchronous mode. The error message of the fault detection function will display here. For the fun display function, we use 3 JK flip-flops to produce an asynchronous counter so that we can produce the sequential lighting of test LEDs. We use a clock generator and the preset input, clear input, and the decoder 3 to 8, and also the output binary display and the output hexadecimal display, and test LEDs, and also the text box. To activate this fun display function, you need to ensure that preset and clear are both equal to 1. And then we need to ensure that the counting sequence is start from 0. And then we can enable the clock animation. The fun display is like this. For the connection between the computers in Lab A with the computers in Lab B, the clock generators are the data source of those computers. We use the multiplexer 8 to 1 and also the demultiplexer 1 to 8 here. We also use the output hexadecimal display and also the output binary displays. Let me show you how it works. Firstly, we need to select one computer and on it in the Lab A. and also on the computer in lab B. Let's say if I want to select the last computer in lab A and also the last computer in lab B. And also we need to select which line that we need to transmit the data. I select 7 here because it's the last computer here. And also I select the 7 here. So the data will be transmitted when the clock is triggered. For the password comparator function, we use 4 4-bit comparators and 4 input hexadecimal. We set the A0 to A3 values by connecting them to the high level or low level input. We also use the AND gate, so only when all passwords we enter are correct, the circuit will work. When we enter the correct password, which is 2638, 2638, the lighting LEDs indicates that we enter the correct password. For the transmission mode function, we use the input hexadecimal, the decoder 2 to 4, and the output binary display. We need to select 1 to ensure that our transmission mode is in simplex mode. For the counter comparator function, we use the input hexadecimal and the 4-bit comparator in order to compare the binary values of the maximum packet transmission and the set binary values. For example, when we select the maximum packet is 7, so the counter comparator will compare whether the counter state is same with the maximum packet or not. For the countout function, we use 3 JK flip-flop pads. Because we need to transmit the 3-bit data, we connect J and K inputs to the high-level input to become to the T flip-flops. We also use the preset and clear input to control the counter to be in the synchronous mode. We also use the output binary display and the output hexadecimal display to display the counting sequence. Firstly, we need to set preset and clear both equals to 1. And then we need to make sure the counting sequence is start from 0. If the counting sequence is not start from 0, we can just clear and then we set again the synchronous mode. In synchronous mode, the counter will start counting when the clock is triggered. For the clock enable function, the first line is connected to the connection between computers in lab A and computers in lab B. The second line is connected to the password comparator function. The third line is connected to the ready button. The fourth line is connected to the counter comparator function. And the fifth line is the push button. When we push it, the circuit will work. The last line is connected to the transmission mode function. The clock enabler function will work only when we connect the computers in lab A with lab B, when we enter the correct password, when we push the ready button, we determine the maximum packet transfer, we push the push button, and also we determine the transmission mode is in simplex mode. For the monitoring packet transfer function, we use the test LEDs and text box to check our conditions. When the powers of computers in lab A and the powers of computers in lab B are on, the test LED will light up. When we determine the mode transmission function is simplex, the test LED will also light up. When we determine the packet transmission, the test LED will also light up. When we enter the correct password, we will light up the test LED. And the last one is when we set the ready button to 1, the test LED will also light up. For the fault detection function, one of the functions is to detect the transmission error from lab A to lab B. When the transmission is failed, the message will be displayed like this. Indicates that the transmission is failed. When the transmission is successful, the display message is like this. The message is displayed between successful and failed because we have the push button. But this one indicates that we can transmit the data successful. The next one is to detect the computers in lab B display port. We use a NOT gate here to connect to each output binary display of each computers in lab B. The next function is to detect whether the counter is stopped counting or not. We use 3 D flip-flops to track the outputs of the T flip-flops. The wire is connected to the Q0, Q1, and Q2. If the counter stops counting, the test LEDs will light up. This one is to check the counter fault. We compare again the binary values of the maximum packet transfer with the set binary values. If they are not the same as the comparator output, the test LEDs will light up. The last one is to ensure that the counter is in synchronous mode. The test LED will light up if we set 1, 0, or 0, 1, or 0, 0, because it is not in the synchronous mode. The text box below here is to display the error message. The test LEDs will light up when the errors are detected. This one is if the counter is not working in the synchronous mode. This one is for comparator fault, the counter fault, the computer on lab 2 display fault, the computer on lab 1 transmission fault. Okay, let us start the circuit. To start the circuit, we can start from the fun display function. We need to set preset and clear both equals to 1 to ensure that the asynchronous counter will work in the synchronous mode. And then we need to choose a computer in lab A and also a computer in lab B. By choosing the bit select here, we can determine which computer we want to choose. Let's say if I want to choose the last computer in lab A and also the third computer in lab B. I choose 2 because it starts from 0, 1, 2, so the third computer is 2. I must on the computer in lab A and also on the computer in lab B. The lighting LED means that I already on the computer in lab A and also on the computer in lab B. Next, we need to enter the correct password, which is 2, 6, 3, 8. The lighting LED indicates that we enter the correct password. We on the ready button, let the ready button equals to 1, and we need to determine the transmission mode, which is the simplex mode. We need to determine the maximum packet transfer, which is 7. And also we need to let the preset and clear equals to 1 in this countout function. Ensure that the counting sequence is start from 0. Then we can enable the clock animation. We also need to push the push button so that the data will be transmitted. And look at here. When I push the push button, the data is being transmitted. When we reach the maximum count, although we push the push button, the data will not be transmitted. You can look at here again. The data will not be transmitted. Let's try again. At this time, I want to choose the 7 computer here in lab A and also the last computer here in lab B. And then we need to select the bit select. We need to select the 6 here and also the 7 here in lab B. Ensure we enter the correct password. We push the ready button. We determine the simplex mode. This time we can also set the maximum packet transfer to 5. Make sure the counter is in the synchronous mode. Oh yeah, we need to clear the counter so that the counting sequence is start from 0. And then we can push the push button so that the counter will count from 0 to 5. 1, 2, 3, 4, 5. Look at here and here. The transmission successful message will be displayed. 1, 2, 3, 4, 5. To monitor this function, we can see here, if the test LEDs are light up, so we can know which error is detected. These 2 errors are occur because we have the push button. Only when we push the push button, the error will be disappear. Let's see. We can see here, 1, 2, 3, 4, 5. Yeah, so in conclusion, when we push the push button, the lighting of the LED will be disappear. But if we left our hand, the LED will be light up. And then we can see here, if the maximum packet number is equals to the counter state, the test LED will be light up. 6, 7. Okay, so means that we have no error in this packet transfer function. That's all from our demo circuit. Thank you.
As for the conclusion, to sum up, our system is easy to handle and user-friendly. This project gave us a valuable learning experience that allowed us to apply theoretical concepts to a practical system. We mainly use multiplexers, demultiplexers, and basic gates to enable data transmission between Computer Lab A and Computer Lab B. While using a comparator for password design for security, Although we faced many challenges at first, we successfully overcame them and enhanced our problem solving and communication skills. This project has not only boosted our confidence, but also motivated us to continue improving our knowledge and exploring more advanced applications in digital logic. Thank you.
That's all from our presentation, and we are from Group 2. Thank you.